Hello, everyone. I hope you have had a nice long weekend. We are back, and this week we are going to work our way through chapter 9. That's really talking about the second law of thermodynamics. Okay, so in the last chapter, we were really working to understand how dE is equal to dW plus dQ. And so we're saying that the change of energy of a system is equal to the work done by the system or on the system plus the heat transferred. And so we're saying that there's really these two forms that energy can take, work and heat. And the efficiency of any system is the work that we get out divided by the heat that we put in. And so what we have is a cold system and a hot surroundings. And the heat of the surroundings is very random. It's going in all directions. And so the surroundings are not just heating the system, but they're heating themselves and the surroundings of the surroundings. But as we put heat into the system, that heat energy of the system also is random. But as the system expands, that work that is done is not random. And so that work that is done happens that we have to move, if the system is expanding, if it's expansion work, we have to move the particles of the surroundings out of the way in a directional motion. And the result of this directionality difference between heat and work is that you cannot fully transform heat into work. So we cannot get all of the energy back as work whenever we add heat to the system. This is why heat engines, like your car, are not very efficient, because we are trying to convert heat into mechanical work, and that transformation, due to the randomness of heat, is not super efficient. And so we work to try to improve our efficiency, but we're never going to get something that is 100% efficient. Okay, so this starts to bring us to the physical meaning of entropy, because if we cannot fully convert heat into work, then that tells us that there's something else going on, that we have some other form of energy that is needed to be able to explain these processes. So if we take two materials separated from each other by a rigid heat conducting wall, and these are isolated from the rest of the universe, they are each in equilibrium, so their temperatures and their volumes are not changing, but they are not in equilibrium with each other. And so B is hot and A is cold, or colder than B. We ask ourselves, as time progresses, what happens? Well, we see this all the time with pouring hot coffee or tea into a mug, or putting cold water into a glass. We watch what happens whenever the system and the surroundings, or in this case, two systems, are not at the same temperature. Well, and so we know what happens. Eventually, the two systems become the same temperature. Our coffee becomes the same temperature as the room. Our cold ice water becomes the same temperature as the air on a hot summer day. And this really is because of the second law of thermodynamics. The second law of thermodynamics says that for any process in a system totally isolated from its surroundings, the macroscopic entropy measured over the entire system can never decrease. And so this tells me that the total entropy is going to always be greater than or equal to 0. This is the second law of thermo. So just like the first law of thermo, it's really easy to state and much harder to understand. And so we're going to take the next several videos to really try to understand what this means and the implications of it. Okay, so let's think a little more about entropy. We spent a long time talking about microstates and entropy and how we work to figure out the Boltzmann distribution and all of that. But now we need to try to think of this a little more from a bigger perspective, from the full system. So as the energy increases, the number of microstates increases. Now, the energy is conserved. And so the energy of the system and the energy of the surroundings cannot vary independently. They're connected to each other by the first law of thermo, that the total energy is equal to the energy of the systems plus the energy of the surrounding. As the energy of the system increases, the number of microstates of the system increases, while the number of microstates of the surroundings decrease. So this is a connection of really sort of this idea of energy and microstates at the same time. So what are we looking at? Down here in our diagram, I am at low energy for my system, and I'm at high energy for my surroundings. And so there are very few microstates in my system, but there are lots and lots of microstates in my surroundings. As we transfer the energy, where now I have high energy of my system and low energy of my surroundings, the microstates transfer. So now my surroundings have fewer microstates and my system has more. So the number of microstates of the universe will be maximized at some system energy. So when we're talking about universe, we are thinking system plus surroundings. And so there is some energy at which the number of microstates is at a maximum. And that's the total microstates, the universe microstates. This is what we call equilibrium. And really what we are going to be doing is we are going to be working to understand equilibrium. Okay, so back to understanding our reservoirs. If we think way back, we know that the entropy is equal to K log omega, where omega is the number of microstates. So to find the maximum entropy with respect to the energy, so if we wanted to find that point where things were at a peak, we would need to take that derivative and set it equal to 0. This is how we find maximum. So if we do that, And so in this, we're basically taking the partial of S with respect to E. Let's do actually E and not epsilon. But we're going to ignore this K because remember, it's just a constant. And we set this equal to 0. With some algebra, we can show that the maximum number of microstates occurs when the sample and the reservoir have the same temperature. So when thermal equilibrium has occurred. So for isolated systems, the entropy will increase until equilibrium is reached. Spontaneous processes are processes that increase entropy. Once equilibrium has been reached, the entropy remains constant. And so really, if we start a system here, that entropy is going to increase until it is maximized and equilibrium occurs. Okay, so stay tuned. In the next video, we're going to go over some relationships and work to make sure that we really understand systems surrounding universe and how the vocabulary that we use around entropy.